This is Math 105, Section 2.4. We're going to talk about average rate of change in this section. Pretty short section here. So we talk about average rate of change. One way to look at that is look at speed. So let's say you go 120 miles in 2 hours. Okay, and you look at your average speed. Well, your average speed is just how many miles you went in how many hours. So 120 divided by 2 is 60 miles per hour. So that's kind of the most obvious example of a rate of change is you're reading on your speedometer that you're going 60 miles per hour. So if you travel 120 miles in 2 hours, you went 60 miles per hour on average over those 2 hours. Okay, so let's suppose you take a car trip and record the distance that you travel every few minutes. Okay, the distance is a function of time. So distance traveled is a function of time. So we can say S of t is total distance traveled at time t, where if you're going forward, that S will increase. If you're going backwards, that S will decrease. Okay. So think of t as like your input, your x, and S as your output, your y. Okay, so here's a graph of S versus t. For example, this function. You can see when we start, our S is 0, and as time goes by, our S is increasing. S is the y here, so it's going up. So as time goes by, our S is increasing. Now notice that as time goes by, sometimes the S is increasing faster, and sometimes it's increasing slower, and that means that our speed is increasing if it's increasing faster. Okay. So let's say we want to look at our average rate of change between t equals 1 and t equals 4. That would be the slope between those 2 points. Okay, that would be how much S changed as t changed. So t changed 3 hours, and then our distance traveled was 150. So we could say our average speed was 150 over 3. So based on that graph, we have traveled a total of 50 miles after 1 hour. We did 75 miles after 2 hours. That would be our S value there. And 140 miles after 3 hours. Okay. If we want to find our average speed between any 2 points on the trip, we divide distance traveled by the time elapsed. Okay. So it's basically your slope there. Okay. So let's say you want your average speed between 1 p.m. and 4 p.m. Okay. Time elapsed is 3 hours, 4 minus 1. Okay. To find the distance traveled, subtract the distance at 1 p.m. from the distance at 4 p.m. So we take 200 minus 150, or 200 minus 50 to get 150. Okay. So our time is 3 hours, and our distance traveled is 150 miles. And then we just divide. So we're looking at average speed would be distance traveled over time elapsed, so that's 150 miles over 3 hours, which is 50 miles per hour. Okay. We can use function notation here. This would be S of 4. That's the S value at t equals 4. S of 1, the S value at t equals 1. So take the difference in the S's divided by the difference in the T's. Okay, so that gives us that 50 miles per hour. So that means that average rate of change is, on average, between hour 1 and hour 4, we traveled at a rate of 50 miles per hour. Now, it's important that we say on average because we're talking about average speed, not constant speed, because our speed changes as time goes by. So let's say we want to look at the average speed between 2 p.m. and 3 p.m. So we take S of 3 minus S of 2, which is 140 minus 75, over 3 minus 2, t equals 3, t equals 2. So 140 minus 75 is 65, over 1 is 65. So we traveled between 2 p.m. and 3 p.m., or t equals 2 and t equals 3, at an average of 65 miles per hour. Okay, so our average rate of change of a function between x equals a and x equals b is just the slope. So it's the change in y over change in x, or f of b minus f of a, the y values, over b minus a. Okay. Now we talk about the concept of a function looking as like a curve. We're looking at a curve as a representation of a function. What we're doing is we're looking at 2 points on that curve, or 2 points on that function. And when you have a line that crosses a function at 2 points, we call that a secant line. So that dotted line segment is called a secant line. Okay, and what we want to do is take, if we want the average rate of change between those 2 points, is take the slope of that secant line. So all we're doing is taking the slope between these 2 points. So change in y, f of b minus f of a, over change in x, b minus a. And that's how we get our average rate of change there. Okay. So that's all you're doing is basically taking the slope between 2 points on a curve. Okay. Okay, so let's look at this function. F of x equals x minus 3 quantity squared. And this is our graph of that. This is just x squared moved 3 to the right. Okay. And let's say we want to know the average rate of change between x equals 1 and x equals 3. So that between these 2 points, and this is the secant line here. And then we'll look at between x equals 4 and x equals 7. And there's x equals 4, x equals 7. And there's our secant line there. So we'll look at those two. Okay, so for a, we're going to take f of 3 minus f of 1 over 3 minus 1. So f of 3 is 3 minus 3 squared. Remember, our function is this, is f of x equals x minus 3 squared. So we're plugging into that function. So we plug in 3 to our function, we get 3 minus 3 squared. And then we plug in 1 to our function, we get 1 minus 3 squared. This is just 0. And then minus, this is 2 squared. So 0 minus 4. And then 3 minus 1 is 2. We're looking at our change in x there. So minus 4 over 2 is minus 2. So we can say on average, this function changed at a rate of minus 2 between x equals 3 and x equals 1. Okay, and our part B, we're looking at between 7 and 4, right? And again, our function is f of x equals x minus 3 quantity squared. Okay, so we look at average rate of change between x equals 4 and x equals 7. Okay. So we're going to take f of 7 minus f of 4 over 7 minus 4, which is 7 minus 3 squared minus 4 minus 3 squared, or 4 squared 16 minus 1 squared 1 over 7 minus 4 is 3. So 16 minus 1 is, sorry, that should be, 15 over 3, which is 5. So here our average rate of change is 5. Okay, for a linear function, f of x equals mx plus b, y equals mx plus b, average rate of change is just m, is just our slope. The reason is because you're taking a slope between 2 points, and when you do that, you're using the same line. Okay. So we can also say if a function f has a constant average rate of change, that it never changes, then it must be a linear function. Okay. So if that average rate of change is always the same, that means that your function is linear because the secant line is the line itself, which is the function. Okay. So for something like f of x equals 3x minus 5, a linear function, if we want to take the average rate of change between any 2 points, we can do it, finding the slope, but we're going to find that slope is going to be 3. So let's do that. So between 1 and 0, we take f of 1 minus f of 0 over 1 minus 0, which is 3 times 1 minus 5 minus 3 times 0 minus 5. Remember, our f of x equals 3x minus 5 is our linear function. Okay. So 3 times 1 minus 5, 3 times 0 minus 5. This is minus 2, this is minus 5. So minus 2 minus minus 5 is plus 3 over 1. 1 minus 0 is 3. So that's for the between 0 and 1. Now let's look between 7 and 3. So we take f of 7 minus f of 3, average rate of change, over 7 minus 3. So 3 times 7 minus 5 is 21 minus 5 is 16. Then 3 times 3 minus 5, 9 minus 5 is 4. And then divided by 7 minus 3 is 4. So we have 16 minus 4 over 4, which is 12 over 4. Again, we get 3 as our slope or average rate of change, okay, between those 2 points. And then finally, we're going to look at between x equals a and x equals a plus h, where a is some number on x, on our x-axis, and a plus h is some other x value, where we're adding h to get our next value. Okay, so you can kind of think of just, those are 2 random points where their difference is h, because if I take a plus h minus a, I get h. Okay, so there are any 2 points on our function, and we're using a linear function here. So f of a plus h minus f of a over a plus h minus a. Okay, so we're going to actually do, put it into our function, which is, again, f of x equals 3x minus 5. So we're going to put a plus h into our function instead of x. So that would be 3 times a plus h minus 5 minus 3 times a minus 5. That would be f of a. Okay. And then we take a plus h minus a. The a's cancel and we just get h. But distributing the 3 here, we get 3a plus 3h minus 5. And then minus 3a plus 5 because we have a minus. Okay, so the 3a's cancel here. The 5's cancel. So we end up getting 3h over h, which the h's cancel here and we get 3. So we've actually proven that the slope is always, or the average rate of change is always the same for this function between any 2 points, because these do represent any 2 points. We can say a is any point in the domain, and then a plus h is some other point where h is some, positive number, or we could say negative number, but h is some real number. Okay, so we're looking at a different point on that line. Okay, and when we take the average rate of change, take the slope between those 2 points, and a linear function, we get the slope. So the slope is 3, right? So whenever you take the average rate of change on a linear function, you always get the slope of that line. Okay, so that's it for section 2.4. Make sure when we're talking about average rate of change, we're just taking the slope between 2 points, right? But that we understand what that means. That we're saying on average between, for example, between x equals a and x equals a plus h, the function changed by this rate between those 2 points. Okay, so we say on average that's the change. Okay, okay.